Okay, guys. Next, we want to talk about the substitutions in double integrals, which is very important. Listen very carefully. Just like single integrals, for double integrals, we can also use substitution to make the calculation of integral easier. And when we use substitution, we may even get an easier region for integration. But before that, let me quickly give you an explanation that when we are using substitution in double integrals, what it means. What is it actually? Look at this graph. You can see we have two-dimensional space. This two-dimensional space represented by u and v, and we have another two-dimensional space represented by x and y. Okay. Look at here. When we use the substitution in the double integral, it means we have a map or mapping from UV plane to XY plane, and conversely. Actually, we have an one-to-one map. Okay, we have a one-to-one map from UV plane to XY plane, and conversely. So this map or mapping, you can see, maps every point like u and v from here to a point here like x and y by these two equations. Like x and y are functions of u and v. You can see x equals g of u and v, y equals h of u and v. So like this, we are going from here to here. And conversely, the inverse of this map maps every xy to u and v, to one pair of u and v here. So this is actually the meaning of the substitution. So when we say we are using substitution in double integrals, it means we have a one-to-one map between these two spaces, between xy uv plane and xy plane. Then in particular, by using like two equations like this, x equals g of u and v and y equals h of u and v, every point like u and v is mapped to a point like x and y here. And of course, a region, this is a rectangular region, like g is mapped to this region r in xy plane. Okay, so like when we use this substitution, of course, we are given a function of x and y. So when we put the value of x and y in terms of u and v, you can see it. This will be a function of u and v. So we will integrate of this function with respect to u and v on g here. You can see like the substitution might make the region easier. Like R here has no regular shape, but G has a regular shape, is rectangular, is rectangle. Okay. So before we give you the formula of substitution, and I mean when we use substitution, how to set up the integral after substitution, look at this example. You can see here in UV plane, we have a rectangle here. Okay, rectangle G. And in XY plane, we have this parallelogram actually, which is bounded by y equals 0, y equals 4, y equals 2x, y equals 2x minus 2. And here we have this rectangle. V equals 0, v equals 2, u equals 0, u equals 1. So look at here, when we use this substitution, when we take x to be u plus v and y to be 2v, using this substitution, this region R is mapped to Okay, here they said from UV to X5. Okay, when we use this substitution, this region G, okay, is mapped to R. Okay, when we use this substitution. Here X and Y are functions of U and V. So this rectangle G is mapped to this parallelogram R. And of course, it means so we have a map from here to here. This map has an inverse which maps R to G. How to do that? If we use these two equations, okay, it means simply we take the inverse of these two equations. So if using these two, we can find U and V. Using this, we can find U and V. If U is 2x minus y divided by 2 and V equals y divided by 2, then it means we are having the inverse of this map, which is from here to here. Okay, so the inverse of this map, which is from here to here, by these two equations maps the region R to G. Okay, but actually when we use substitution, okay, we usually take X and Y as a function of U and V, and we are going from U and V to XY. Now next, look at the formula. This is how we set up the integral when we use substitution. Look at here. Let's say we are given a double integral of f of xy dx dy or dA on R. And let's say we use a substitution like x and y are function of u and v. So x is g of u and v, y is h of u and v. So we put here the value of x and y in terms of u and v. So this will be a function of u and v. And we have something here that be careful not to forget it. This is the absolute value of j of u and v du dv. What is this j? This j of u and v is called Jacobian determinant. Okay, Jacobian determinant, and it's defined to be like this determinant. Look at here. The first row, the partial derivatives of x with respect to u and v. Look at here, the derivative of x with respect to u and with respect to v. And second row, the partial derivatives of y with respect to u and v. Okay, we calculate this, we put here, and this is absolute value. And of course, we have to describe the region G, and the order of this order du, dv, or dv du depends to the description of region G in UV plane. Then we go ahead to calculate this integral with respect to u and v. So one more time I repeat, when we use substitution, we use this formula, and do not forget this Jacobian. This is the absolute value of Jacobian. Okay, next look at here. Before we talk about this fact that when we say the double integral in polar form, actually we are using a kind of, if you remember I mentioned this earlier, when we are using double integral in polar form, we are actually using a kind of substitution. But before I discuss about this page, okay, I would like to discuss this example for you. Then we will be back to this double integral in polar form. So this is the page 46. I'm gonna discuss this example. Look at here, we have a double integral of 2x minus y divided by 2 dx dy over this region R. So you can see the region R is described yes, in the form of case 2. You can see y is from 0 to 4 and x is from, okay, here if we divide both sides by 2, so x is from y over 2 to y over 2 plus 1. Okay, so we want to calculate this integral using the substitution. But what is the substitution? Okay, you may worry that how we find the substitution. I understand this could be complicated. You need to practice a lot, but do not worry. In the exam we will give you the substitution. So it means the substitution that we are going to use to solve this integral is this one. If you back here is this. It means we are going to use x equals u plus v, y equals 2v. That under this substitution, the region R in xy plane is corresponding to the region G in uv plane, that you can see. Okay, here you can see here. So we are going to use this substitution that I'm gonna do for you. Okay, so take a look at this here. So we have the integral of 2x minus y divided by 2 dx dy. We want to solve it by this substitution. X equals u plus v and y equals 2v. And under this substitution, the region R is corresponding to the region G in UV plane. Okay, so let's do it here. So now, according to this theorem, look at here, let me remind you one more time. So we have to put the value of x and y in terms of u and the absolute value of the, okay, sorry for interruption, the absolute value of Jacobian determinant du, dv or dv du. This order depends on how we describe the region G. Okay, so let's follow this formula and do it. Okay, here this equals, so we are using substitution, right? So we get a double integral in terms of u and v on region G. Later we will put the description of region G here. So what is x? Look at here, x is u plus v. So here we have 2 times u plus v minus v, well, sorry, minus y. Y is 2v. Minus 2v divided by 2. Then do not forget, here we have the absolute value of the Jacobian. We have to calculate the Jacobian and put here J of u and v du dv or dv du. Later we can decide about the order of integration. Actually this integral with respect to u and v is being calculated on G, and G is rectangular. So du dv or dv du. We can switch the order of integration, right? Okay. Now we have to calculate the Jacobian here. Okay, this is the Jacobian determinant, right? Okay. The determinant refers to the partial derivative of x with respect to u and v. The second row, partial derivatives of y with respect to u and v, as you can see here. Okay, let's calculate. Okay, the partial, the derivative of x with respect to u, you can see here, with respect to u. This one 0, 1. So we have 1. Derivative of x with respect to v. Okay, this is 0 and this one 1. Okay. Derivative of y with respect to u, you can see y is independent from u. So the derivative of y with respect to u is 0. Okay, and derivative of y with respect to v, 2. So if we calculate this determinant, 1 times 2, 2 minus 1 times 0 is 0, so The Jacobian determinant is 2. Now we have to put this 2 here, and since 2 is positive, you can remove the absolute value. Okay, so let me erase here, then we continue the calculation. Okay, let's continue. If you remember, we calculated Jacobian was 2. Okay, let's put it here. So this equals integral on G. Look at here, 2u, okay, this 2u. 2v minus 2v is 0. So left only 2u divided by 2, and this is our Jacobian. Our Jacobian was 2. So the absolute value of 2, or modulus 2, which is equal to 2. So this 2 by this 2 simplified, only left 2u du dv. Now about the region G. Look at the region G here. Region G in UV plane is a rectangle. Okay, so we can calculate the order in the order of du dv or dv du. You remember, when the region is rectangular, the order of the integration doesn't matter. So we can go ahead and solve it in this order, du dv. So it means this one will be the lower limit and upper limit for u, and this one for v. Look at here, if you look at the picture, u is from 0 to 1, v is from 0 to 2. So we put here u is from 0 to 1 and v is from 0 to 2. So now we can go ahead and solve the integral. So we have integral from 0 to 2. This is for v. Okay, what is the integral of 2u du is with respect to u? Is u squared. It's easy. U squared. Okay. U squared from 0 to 1 dv. So this is easy. Let me continue here. So the answer to this one is 1, because when u is 1 square minus 0 square 0. So 1 minus, so this becomes 1 minus 0. So this is 1. Okay, this is 1. So left only integral from 0 to 2 dv. Okay, and this one is easy. This means v from 0 to 2. So the answer is 2. Okay, as you can see here, the answer is 2. Look at the next page. Yes, here integral 2 du dv, u squared from 0 to 1, which is 1, and left integral dv from 0 to 2, which is 2. So this is the answer. Okay, now look at here. When we say the double integral in polar form, actually we are using a kind of substitution. It means for our substitution we are using polar coordinate system. So x is so it means actually we have two plane, xy plane and r theta plane. Okay, xy plane and r theta plane. So x is a function of r and theta, which is r cosine theta. Y is a function of r and theta, which is r sine theta. And the Jacobian of this particular substitution you can see here, with partial derivatives of x with respect to r and theta, and partial derivatives of y with respect to r and theta, if we calculate, is r. So when we have a double integral of f on r, when we use polar coordinate system for our substitution, so here we put the value of x is r cosine theta, y is r sine theta, and the absolute value of Jacobian. And the Jacobian for the determinant of Jacobian determinant here, the Jacobian for this particular substitution is always r. So here we have to put r. But we try to choose r to be positive. Okay, so if we try to choose r to be positive, we don't need to put absolute value. So this equals f of, okay, here is r cosine theta, r sine theta, r dr d theta. So now let me remind you something. Do you remember when we calculate the double integral in Cartesian system? dA is dx dy, right? But in polar system, dA is r dr d theta. So now you know where this r is coming from. Actually, r is the Jacobian of this substitution when we use polar coordinate system. Regarding this, let me remind you something. Here, do you remember on page 39 of your lecture note, we had this example that we already discussed. We had this integral, double integral, that we converted to polar. But actually, when we convert a double integral from Cartesian system to polar system, it means we are actually using this substitution. We take x to be r cosine theta, y to be r sine theta, and the Jacobian of this substitution is r. Okay, so here you can see exponential minus x squared plus y squared is r squared. Okay, and the absolute value of Jacobian dr d theta, and these are the lower limit and upper limits for g actually. Okay, here we have r, here the region is g, which is described by this. R is from 0 to infinity, theta is from 0 to 2 pi. And this equals, okay, look at here, the Jacobian is r, right? Okay, and r is positive from 0 to infinity. We don't need to put absolute value. We can remove the absolute value, so we have r dr d theta. The rest is the same because we have done this. Let me show you first with respect to r, then with respect to theta. Here, you can see, if you remember, we have done this. And we get the answer 1/2. Correct? So that's it. Okay, now look at here. I prepared some example for you. Okay, this is our example. We want to calculate the double integral of 2xy dx dy on region R by using this substitution. Let's say polar substitution. What is region R here? This is our region R in yellow color. You can see this region R actually, okay, is the area bounded between two circles centered at origin of radius 1 and radius 2, and theta is from pi over 4 to pi over 2. So this is R. Okay, this is R. Now we want to use substitution, polar substitution. It means this. So this equals the double integral 2 times, this is x, r cosine theta, this is y, r sine theta, and the absolute value or modulus Jacobian. And Jacobian of polar substitution is always r. dr d theta. But what is g? What is g? G is the description of this region R, okay, using polar coordinate system. So when we use polar coordinate system, do you agree with me, to cover the region R, we can say, look at here, to cover, theta is from pi over 4 to pi over 2, from pi over 4 to pi over 2, and R is from R is from 1 to 2. So it means actually this region R is corresponding to this rectangular region in two-dimensional space represented by r and theta, which is a rectangular region. Look at here, r is from 1 to 2, theta is from pi over 4 to pi over 2. Okay, so you can see when we use polar substitution in two-dimensional space represented by r and theta, we are going to calculate the double integral with respect to r and theta on a rectangular region, which is much easier than this. So you can see by substitution we may get the easier area for integration. Okay, rectangular. Okay, so this is our g. This is our g. So here we have to put instead of g, for g, okay, r is, we can see, from 1 to 2, theta is from pi over 4 to pi over 2. Pi over 4 to pi over 2. So let me erase here, we continue. Okay, so you can see here, this equals this integral with respect to r and theta. So g is this. G is here. So the description of g, for r we have r is from 1 to 2 and theta from pi divided by 4 to pi divided by 2. And here, look at here, we have r times r, we have r squared. 2 cosine theta sine theta equals sine 2 theta. And this is our Jacobian, the absolute value of r, and since r is positive we can remove the absolute value. So this is our Jacobian, r dr d theta. So we have the integral, this r times r squared is r cubed sine 2 theta dr d theta. So we are going to integrate first with respect to r, then with respect to theta. So since the space is not enough, we are going to move up here, so I have to erase this one. Okay, so we have integral from pi over 4 to pi over 2, integral from 1 to 2 sine 2 theta times r cubed dr d theta. So first with respect to r, so you can see the integral with this r cubed dr is r4 over 4 from 1 to 2. Okay, so this equals integral from pi over 4 to pi over 2 sine 2 theta. So the value of this one is 2 to the power of 4 minus 1 to the power of 4 divided by 4, and this means 16 minus 1, it means 15 over 4 divided by 4. So this is a constant, so comes here. So left integral from pi over 4 to pi over 2 sine 2 theta d theta. So next we are going to calculate this integral. So let's move up here. Okay, now we have to calculate this integral. Okay, this equals 15 over 4. Okay, what is the integral of sine 2 theta? If you use substitution and you take 2 theta to be u, the integral of sine 2 theta equals minus 1/2 cosine 2 theta. Cosine 2 theta from pi over 4 to pi over 2. And let's continue here, and this equals, okay, this time this becomes minus 15 over 8. So the value of cosine 2 theta when theta is pi over 2, so becomes cosine when theta is pi over 2 times 2 pi minus cosine when theta is pi over 4, so 2 theta become pi over 2. Okay, so this equals minus 15 over 8 times cosine pi is minus 1, cosine pi is minus 1 minus cosine pi over 2 is 0. So the answer becomes 15 over 8. So the double integral of this function here on region R, we use substitution, so we get a double integral with respect to r and theta on this rectangular region on r theta plane, and you can see we calculate. The answer becomes 15 over 8. Okay, let's see another example about the substitutions in double integrals. The example of page 49. You can see we are given a double integral, the square root of x plus y times y minus 2x squared dy dx, and this is the region R, you can see here. x from 0 to 1 and y is from 0 to this line. The equation of this line is 1 minus x. We want to use this substitution to solve this integral. Firstly, if we use this substitution, you can see by this substitution, let me show you. By this substitution, the region R is mapped to this region G in UV plane, which can be described. Look at here. This is the line V equals minus 2u, and this is the line V equals u. So we can say V is from minus 2u to u, and u is from 0 to 1. Okay. Anyhow, so let's look at here. So this is our integral. Okay. If you use this substitution I have done here for you, it's easy to calculate. X plus y, you can see x and y. X plus y becomes u. And y minus 2x becomes v. So v squared. So x plus y equals u. You can calculate. It's easy. I leave it to you. And y minus 2x, using these two equations, y minus 2x equals v. So v squared. The Jacobian dv du. Okay, dv du or du dv. It depends how we describe the region G. But you can see here, as I mentioned, since v is between two curves, so I'm gonna solve it in this order, dv du. So first we have to, do not forget, we have to calculate the Jacobian. So you can see the determinant of the partial derivative here with respect to u and v, and the derivative of x with respect to u is 1/3, with respect to v is minus 1/3. Derivative of y with respect to u is 2/3, and derivative of y with respect to v is minus. Sorry, there is a mistake here. I have to correct this. So derivative of derivative of y with respect to, this one should be, this one should be 1/3, right? Let's check it again. So this is correct. 1/3 minus 1/3, 2/3, 1/3. Now, so we have to fix this. We have to fix this. So now, if we calculate the determinant, 1/3 plus 2/3. So the determinant will be, so let me correct this. So this will be 1/3. This will be 1/3. Then we calculate. Now we have to put it here, and also the description of the region G. So let me erase here, then we continue. We need some space. Now let's solve the integral. Look at here. So this equals the square root of u is u to the power of 1/2, and this one v squared, and the Jacobian we calculate is 1/3. So absolute value of 1/3. dv du, and look at the description of region G. Let me show you one more time. You can see v is from minus 2u to u. From minus 2u, from this line to this line, lower curve to upper curve. And then u is from 0 to 1. So v is from minus 2u to u. U is from 0 to 1. So here you can see u and for v. So we have the integral, and look at here, this is positive, we don't need to absolute value. So this equals u to the power of 1/2, 1/3 v squared dv du. So we start to integrate first with respect to v. So we have integral from 0 to 1. This is for u. So look at here, 1/3. the integral of v squared is v cubed divided by 3 from minus 2u to u du. So we have integral from 0 to 1 u squared. This one 1/3 times 1/3 is 1/9, 1 divided by 9. So the value of v cubed when when v equals u, which is u cubed, minus when v equals minus 2u, so minus 2u cubed du. Now we have to calculate this. Since the space is not enough, let's move up here. Okay, let's continue the calculation. So we have 1/9 integral from 0 to 1 u to the power of 1/2 u cubed minus 2u cubed du. So this equals 1/2 integral from 0 to 1 u to the power of 1/2. Look at here, u cubed minus this minus 2u to the power of 3 becomes minus 8 cubed, and we have one minus here, so becomes plus 8 cubed. So we get 1/2, we get 1/9 integral from 0 to 1, so 8u cubed plus 1u cubed, so 8 plus 1 becomes 9. 9u cubed here times u to the power of 1/2. And then this 9 simplified with 9, 9/9 is 1, and u cubed times u to the power of 1/2 is u to the power of 7/2, or 7 divided by 2. So you know this integral is easy. 1/7/2 plus 1 to the power of u to the power of 7/2 plus 1 from 0 to 1, so becomes 2/9 times u to the power of 9/2 from 0 to 1, so the answer becomes 2/9. As you can see here, this is the answer.